welcome back. And we're going to continue with our discussion of the spread of a data set. How can we calculate the spread? So in our last video, we did many things, but we looked at dataset C and we also had a dataset D that had the same mean and median. So this is why being able to calculate the spread of a dataset is so important. It's really the only difference in data sets that have the same center. So we talked about a couple different measures of spread. The range is the maximum minus the minimum, and it's cool in a pinch, but it's really kind of weak as a measure of spread because it only involves two values in the calculation, and it's the most extreme values. So if the maximum or the minimum or both are like really strange, crazy outliers, then the range of the data set isn't really telling you a whole lot because those values are dominating that difference. So a better measure of spread is IQR, and that is Q3 minus Q1, and that gives us the distance that separates the middle 50% of the data set. It still only uses some of the values, not all of them, in the calculation, but that makes it resistant or robust as a measure of spread. It's not going to be influenced by outliers because these numbers aren't very close to the outliers. They're only the 75th and 25th percentiles. So even if we have crazy outliers, the IQR won't be affected very much. But again, it still only uses some of the values. We'd really like a measure of spread that uses all the values of the data set. And luckily, there is one. It's called the standard deviation. And that might bring back some not so fond memories for those that took the one semester class because it took a while to be able to calculate this by hand. We actually used a table that had several different columns in order to calculate this. And yes, we are going to calculate standard deviation by hand in this video. However, I doubt that you'll be asked to do it by hand, so we will also show how we can use the calculator to find this, but it's important that you know how it's calculated. I feel like going straight to the calculator version of this you would never see where it comes from. And I do think that's important, and I'm not just saying that because I'm a teacher and you're a student and I need to fill time. Trust me, I'm trying to save time wherever I can. But I think it's important that you know how good of a measure of spread this is and why. So, if we're talking about a population standard deviation, so this is going to get the same treatment as the mean did, where we had a population mean and a sample mean. If we're calculating the population standard deviation, remember the mean was mu, that Greek letter. The population standard deviation is also denoted by a Greek letter. This is lowercase sigma, right? We already know uppercase sigma is the sum symbol for when you're adding things together. This is lowercase sigma. And that's if we're talking about a population standard deviation. For a, I forgot what the word sample was for a minute. Please forgive me. If we are referencing a sample standard deviation, we're going to use a lowercase s to denote the sample standard deviation. So, also know that standard deviation, those words are just too big for me and for many statisticians out there. So I will be abbreviating standard deviation almost all the time as either SD or STDEV something, right? That's just, it's too many letters. You know, it happens. All right, so how do we calculate it? Well, I'm not going to go through the different calculations for both of these because just like the mean, the only thing that really changes is You use the sample size in this formula, and you use the population size in this one. There is another slight difference. That's beyond the scope of this course. Let's just talk about how to calculate S. So I want to make sure that I write the formula the way this textbook writes it, because there are some subtle differences between books. That's the formula. Okay? It's kind of intimidating, isn't it? Perhaps, maybe you're not scared. If not, hey, that's great. But we're going to dissect this and see what it all means. Because I promise, it's just a few simple steps that get you to this. I know it looks a little crazy, but we can do it. We're going to calculate the sample standard deviation, S, for dataset C. We're going to go through the steps. And I'm going to show it a little differently than I do in probability and statistics. And again, I don't imagine you'll have to calculate this by hand, given the raw data, because you will have access to a graphing calculator that can do it. But just this one time, with this very short data set, you're going to see how the sausage is made. Okay, so let's go for it. Step 1. So we're calculating S, sample standard deviation. So we're assuming that this is a sample, and like I said, 99% of the time, if we're given a data set, we're saying it's from a sample. Okay, so step 1. We know what this guy is, right? This is X bar. That's the sample mean. We need to be able to calculate the sample mean before we can do anything else. So, calculate X bar. Okay, so for data set C, I believe we already calculated the mean in the last video, but just to recall, X bar C for data set C is, we would add up all those values, 70, divide by 5, and that will give us 50. Okay, so X bar sub C, and really since there's only one data set we're talking about, I'm going to leave out the subscript because I don't want you to get confused. That is X bar. Okay, that's 50. Fantastic. So step 2. If we look inside these parentheses here, you'll see we're taking each of the values. So we're taking each of these separately and subtracting X bar from each of those values. So let's do that. So we are calculating this for each data value. Okay. So we've got 30 minus the mean, 40 minus the mean, 50 minus the mean, that's going to be 0, 60 minus the mean is 10, and 70 minus the mean is 20. So we get these values here. Okay. If you took the one semester prob stats class, then you might think in the table, yes, this was the second column. It was these numbers, right? The first column was these. In the second column, we took each of those and subtracted the mean. Okay, so we've got these differences. So we've got every value that is in these parentheses. What are we doing to these things in the parentheses? We're squaring them. So step 3 is to take each of these values and square it. Okay, so with each step we're getting a little bit closer to our goal. This is what we're calculating now by squaring each difference. So we're taking negative 20 squared. That's 20 times 20, 400. Negative 10 squared is 100. 0 squared is 0. 10 squared is 100. Whoops. And 20 squared is also 400. So we just took each of these values and squared them. Okay. In the ProbStats table, these are the numbers in that third and final column. Okay. So we've calculated this quantity for each of the values from I equals 1 to 5, which is the number of values that were in our data set. What are we doing with all these xi minus x bar squareds? We add them up. We add them up. That's step 4. So by writing it this way, I'm actually possibly making it more complicated than it really is. All you're doing is taking these 5 values and adding them up. But these are the squared differences. Okay, so we've got 400 plus 100 plus 0 plus 100 plus 400. That is 1,000. 1,000. Fantastic. We're so close. We've got almost everything that's inside the square root. We've got all of this. It looks like right now we need to take whatever this quantity is, which is 1,000, and divide it by n minus 1. That's step 5. We're just taking that value and dividing by n minus 1. Remember, n is the sample size. So we're taking this value and dividing by the sample size minus 1. Sample size was 5. Dataset C has 5 values. So that's 1,000 over 4, which is 250. 250. We are so close. We're so close. This is not the standard deviation quite yet, because, as you can see, we still need to take the square root to get the standard deviation. But this number, this number is called the variance. The variance of dataset C, since that's where it came from. Okay? So if we take the standard deviation formula and do everything except the square root at the end, that gives us the variance. Okay? And it's important to know what the variance is. It's essentially the standard deviation squared, right? Because we haven't taken the square root yet. And it has applications throughout the rest of the course. So again, we're never really going to calculate this by hand ever again, but I do want you to see the relationship between the variance, which is this number, and the standard deviation, which is going to be the square root of this number. Okay? The variance is the square of the standard deviation, or conversely, the standard deviation is the square root of the variance. Important to remember. Make sure that's in your notes. But we are interested in the standard deviation, so we just do that last step and take the square root of everything we've calculated here. I've forgotten what the square root of 250 is. I don't know that one off the top of my head. 15.81. So 15.81, so S is approximately 15.81. And that is how I calculate a standard deviation by hand. That took too long. In the year 2020, we can calculate standard deviations faster than that. And we will, in just a minute, learn how to get the standard deviation of a data set using a graphing calculator very quickly. But I thought it was important that you see how this is calculated. Notice, in calculating the standard deviation, we used every single value, right? We added them all up, we subtracted them all, or we calculated the mean by adding them all up. We subtracted all of them, or we subtracted the mean from all of them, right? It uses all the values of the data set, which is something these measures of spread can't say. So, there's a lot up here. If you need to write any of this in your notes, pause the video, do it now. Because I'm going to get rid of it all. Bye-bye. Much better. Okay, so we just learned how to calculate standard deviation. We went through all the steps, and we saw that it uses every value of the data set, which is a good quality to have. Maybe. The IQR was Q3 minus Q1, and we said that it was robust or resistant to outliers because those outliers, if they were to exist, would not figure into this calculation at all. Standard deviation that we just calculated, we saw that every value is included here. So what I want to know is, what happens to this number, this calculation, if there are outliers? There's a data set we've worked with recently that has one. Dataset B, remember? It has that giant number at the end. And it made the mean this big. Let's just conceptualize. We don't have to calculate. We don't have to go through the steps again. But let's just think about what would happen with dataset B trying to calculate standard deviation. X bar is 1,337. Most of the xi's are very small. So when we take this difference, that difference is going to be very large, right? And what are we doing to those differences? We're squaring them. So those large differences become very, very large squared differences. So if we have outliers in our data set, what's it going to do to the standard deviation? It's going to blow it up really, really big, right? The data sets that have the smallest standard deviations have the least spread. They're all very, very close together, the numbers. If you've got outliers, it's going to make that standard deviation much bigger because this difference is big, and then you're squaring it. Okay? Yes, you're dividing by n minus 1. Yes, you're taking the square root, but that difference squared is still going to be ginormous. So not only do outliers make this standard deviation really big, but what does that mean in terms of whether it's robust or resistant to outliers? It's not. And that's bad because we would like to use standard deviation all the time because it does use every value in the data set. So I feel like we've had this argument before. We've got two different measures. One is robust and resistant, but doesn't use all the values. The other one uses all the values, but blows up if you've got outliers. Where did we have that argument before? Oh yeah, mean versus median, right? We have the same strife, the same tension between mean and median, right? The median is robust, like IQR is, but it only uses a few values, like IQR does. Whereas the mean, not robust. Remember what happened with the mean? It's really big if you throw in an outlier, right? Or really small if it were a small outlier, okay? But it uses all the values, like standard deviation does. So we get this nice partnership. We've got median and IQR. They go together very well. They fit together like a glove. And so do the mean and the standard deviation. So when do we use this measure of center and spread? And when do we use this measure of center and spread? When do we want to use these? These are the ones that are robust. They're resistant to outliers or skewness. So if you've got skewness or outliers, you should use these because they are robust. Ooh, I got really close to writing on my actual wall there. My wife would have absolutely killed me if I did that. Okay? If your data set's ugly, ugly meaning it's got skewness, it's got outliers, it's got both, you want to use these measures of center and spread because they're not going to blow up because of those things. If you try to use the mean or standard deviation when you have these problems, you're not going to be happy because this is going to be a bad measure of center. And this measure of spread is going to be really affected by either the skewness or the outliers. You only want to use these if your data set is nice and beautiful and doesn't have either of these qualities. So you want to use the mean and standard deviation when data set is, remember how we like to use the term roughly symmetric? And free of outliers. Okay. Why don't we just always use the median and IQR? Because if we've got a nice distribution and the mean and median are very similar and the standard deviation and IQR are very similar, we want to default to the statistic that uses all the values of the data set. Okay. In a vacuum, I would always want to use these because they use every value. But since these go wonky, if there's skewness or outliers, then we've got a fallback plan, a backup. If our data set is ugly in those ways, if it has those characteristics, we can use these statistics to describe the center and spread instead. So we've always got something we can use. We're never going to use range. We're never going to use the mode. You always hear mean, median, mode. We don't care about the mode. Get out of here, mode. We don't like you. Okay? So now, if I give you raw data values and I ask you to describe the distribution, you'll probably want to make a histogram so you can see the shape. And once you do that, you should know which measures to use for center and spread. If you've got skewness and outliers or one or the other, use median and IQR. If it's a nice, roughly symmetric, no outliers distribution, use mean and standard deviation for center and spread. So I've been teasing it long enough. Let's figure out how to get a lot of these statistics right away using the graphing calculator. Here we go. We're finally going to learn how to do this on the calculator. And the data we're going to use, I chose the U.S. Women's National Team goals per match data that we've used in the past. So we've got our data here. So let me get my calculator up. So that link was from Canvas. We go here, practice tests, mathematics, high school. Start, calculator. All right, so let's do this. You will need to enter the data into the calculator first. So that's in stat edit. And then you'll type your data in. I'm going to do it using the power of editing. Hey, look, all my data is in L1. Fantastic. So once you've got all your data in, it's actually quite simple. You're going to go back to stat, and you're going to go right arrow until you see calc highlighted at the top. And it is on 1var stats. That's what you want. So enter at 1var stats. And if you've got an old school calculator, it'll just say 1var stats on the main screen. And as long as your list is in L1, you can just hit enter again to get what you want. On this window, it'll prompt you for what list to use, and it will automatically put in L1. If your data is in any other list, you can just type in second 5 for L5 or something like that. But my data is in L1, so we'll keep it there. Frequent list, we're going to keep that blank. The only reason you would need to fill that in is if we had data and frequencies in a separate list, and I don't think we're ever going to have data like that in this course. So if you're ever doing 1var stats, use your list, keep that blank, calculate, enter. Oh yeah, this is good. I love this. So it gives us so much stuff. X bar is 3.15. That's our sample mean, right? It gives you the sum of all the X values. So it added up all of these values. Apparently that adds to 63. Cool. And it even adds up the sum of the squared values, just in case you ever need that. I don't think you'll need that in this class. So sample mean is good. It gives you SX and sigma X. Now, if you remember from earlier in the video, these are both measures of standard deviation. But S is if this is a sample, and sigma is if this is a population. Now, we're treating our data here as a sample, just like you almost always will be. So to find the standard deviation of a data set, always look at SX. If you need to put that in your notes specifically, do that. I have had students in the past mistake the two. They never really remembered which one they were supposed to use, and they are different numbers, okay? And they will be a lot, and the bigger the numbers are, the more of a difference there's going to be. So, always use SX unless I say so. So we've got our mean and standard deviation. It gives you n, the number of data values, and it also gives you the minimum value and the maximum value, Q1, Q3, and the median. 1var stats is dope. And I know I sounded really cool saying that, right? 1var stats is dope. It gives you the sample mean, it gives you the sample standard deviation, and it gives you the quartiles, the median, the min, and the max. I mean, at this point, that's pretty much everything you could possibly want to describe a distribution. Let's describe this distribution. Shouldn't we? I think we should. We've still got time. Let's do it. Let's describe this distribution. You might have a tough time until you make a histogram first. That's what I would recommend. So, do you remember how to make a histogram using the calculator? Second, stat plot. We want to turn that first plot on. We want to go to the histogram shape. That's the bar graph looking thing. So that's that one. Our data is in L1. Keep the frequencies at 1. Color is blue, that's fine. Zoom 9. And that's our shape. I believe we've graphed this already. So we knew it was this general shape. Now, before, when I introduced the histogram, I went to window and I messed with it to make it look all pretty. And if you hit trace, the bar widths right now, it goes from 1 to 2.8. I was like, that's messy, and we tweaked it. If we're describing the distribution, this is fine. This histogram tells us everything we need, because all we're really using this for is looking at the shape. What kind of shape is this? It's definitely skewed. Which direction? It's skewed to the right. I'm pointing left, but to you it looks right. Right? Because if we put our little dot at the top of this one and point it towards the length of the long tail, it's pointing to the right. This is a right skewed distribution. Knowing that, what measures of center and spread are we going to use to describe the distribution of goals per match? For center, we're going to use median, and for spread, we're going to use IQR. This is a median and IQR data set because it's nasty. Look how skewed it is. That's not anywhere close to symmetric. If we tried to calculate the mean and standard deviation of this, those would be wildly influenced by these few values out here. So let's use median and IQR to describe this distribution. Do we know what those are? Well, let's go back to one of our stats. Back to the main screen, second quit. Unfortunately, it's gone. I think that's the last thing we actually entered. So if we hit second entry, we get it back. One of our stats L1, fantastic. We could just go back to stat, calc, one of our stats, do it that way too. We were using median and IQR, right? The median is 2. So we would describe the center of this distribution by saying the median number of goals scored by the U.S. women's national team in 2016 was 2 goals per match. Okay? We want to use the IQR for spread. How do we calculate IQR again? Q3 minus Q1. Now, one of our stats, by default, doesn't calculate the IQR for you. You do have to make that difference yourself. But 4.5 minus 1 equals 3.5, not too bad. And if you really want to be a hacker person, you could write a program that calculates the IQR for you. That would probably take longer than just 4.5 minus 1. So take that difference. The IQR is 3.5. So you could say the IQR is 3.5 goals, which shows the spread in the middle 50% of matches, right, in terms of goals scored. What else could we say? We could say the distribution of goals scored per match is right skewed. We already said something about the center. We already mentioned the IQR for spread. Outliers, going back to the graph, we could potentially say, just looking at this, that there's an outlier between 10 and 11.8, and looking at the data set, we can see that number is 10. You could say that that's an outlier. You could even include the value in here, which is the 9. So you could say 9 and 10 appear to be outliers on the high side. And that would be pretty good. Shape is right skewed, median's 2, IQR is 3.5. Possible outliers at 9 and 10. Making sure to include the context at least once. U.S. women's national team goals per match. Okay, I think that's pretty good. The only thing we didn't really calculate is the outliers. We kind of just looked at it and said they look like outliers. So, guess what we're going to do next? We're going to determine how an outlier is calculated and whether a data point is an outlier or not. Yay! Then we'll be able to describe a distribution perfectly. So, make sure you stay tuned in the next video for that. But until then, have a great day.